Hello everyone, this video is going to introduce a WACV paper, Density-Based Flow Mass Integration via Deformable Convolution for Video People Flux Estimation. This research is conducted by National Yangming Jiao Tong University. I am the presenter, Chang-Lin. So first, let me explain what is Video People Flux Estimation. The video people flux estimation, or we can say it video crowd counting, is to estimate the total number of unique people appearing in the video. So unlike the single image based crowd counting, the video crowd counting needs to count how many individuals newly enter at the next frame. For instance, consider these two frames. Each frame displays 3 individuals. However, when estimating the video people flux, the correct count is not 6. This is due to the second and third person appearing in both frames. We must exclude the duplicated count. Therefore, the correct answer is 4 people. Recent work solved the video crowd count problem by 2 ways. The first way is mutual object tracking. This method may encounter the issue of ID switching. The another way is optimal transfer algorithm. The optimal transfer algorithm compares all the half features extracted by local maximum of density map, which may become challenging when people increases. So, our proposed method addresses these 2 issues. We choose a density-based method over MOT method to avoid potential ID switch issues. Instead of comparing all the head features, our method utilizes a flow mask to assess in-out areas efficiently. This is our model architecture. Initially, we employ VGG for feature extraction, followed by the use of the deformable convolution layers for spatial alignment of features from 2 frames. Finally, we apply it to 3 learning objectives: the colorization pre-trained learning, and the flow mass learning, and the density map prediction. In deformable convolution, our primary goal is to align spatial features effectively. The first step in this process involves generating offset maps. Delta PT is the offset map applied to a deformable convolution for aligning the feature map at time t, and delta p plus tau serves the same purpose for the feature map at time t plus tau. Then we can get 2 alignment features, ft tail and ft plus tau tail, after the deformable convolution. In our first training stage, which focuses on colorization learning, we input a colorful frame at time t and a grayscale frame at time t plus tau. Our objective is for the model to predict the color at time t plus tau based on the information from the colorful frame at time t. The model is designed to forecast the color distribution for the grayscale frame. And then we minimize the cross-entropy loss between the predicted probability and the ground truth color distribution. After completing colorization learning, we adapt the model by loading the pre-trained weights to focus on learning density maps and in-outflow masks. We simply use feature primary network and optimize MFE loss to predict density mass, because we aim to compare the performance of our inflow-outflow mass branch with optimal transfer algorithm. Finally, when predicting the inflow mask, we concatenate the spatial alignment feature ft tail with the feature map at time t plus tau, and then go through the decoder. The same procedure is applied when predicting the outflow mask, and then multiply the density map and flow mask can get the inflow-outflow count. and then we optimize our flow mask by the binary cross entropy loss. The ground truth mask is generated by creating a square region with a value of 1 based on the center position of the person's head. To address the excessive overflow of offset for deformable convolution, we introduce a new loss, Intra-Frame head contrastive learning. We choose mutual persons' head feature from feature map at time t and time t plus tau as positive pairs, and the negative samples are chosen from the rest of the head features. Then the Intra-Frame head contrastive learning can be formulated as a follow equation. We use 3 evaluation metrics to compare our method with baselines. The MAE and MSE are commonly used. The WRA weighted relative absolute error is introduced because different video segments have different video lengths. The table displays results on the real data set HT21 using various methods. The underlying number represents the ground truth count for each scene. It is noticeable that the other method yields extreme results in specific scenes. We also implement methods on color synthetic dataset that we generated. In color dataset, we noticed that both ByTrack and BOT sort encounter issues with ID switch in color 15 scene, and the DRNet tends to underestimate the flow of the individual. This is the visualization results on HT21 dataset. We can see that our model can discriminate the inflow-outflow of individuals very well. In highlighted boxes, the red box indicates the area where the individual enter or exit the frame, and the blue box represents areas with minimal movements of individuals. It can be observed that there are noticeable differences in the offset maps within the red box, while the offset maps within the blue box appear to be similar. Similarly, the results are reflected in the color synthetic dataset. The model demonstrates a strong discriminative ability, particularly highlighted in the red box region. We summarize our contribution as follows. The combination of spatial alignment capability of deformable convolution and in-out flow mask distinguish different individuals across frames. Moreover, by effectively integrating Intra-Frame head contrastive loss, we further enhance its discriminative power, enabling better differentiation in densely populated scenes. Thank you for your listening.